Okay, good afternoon. Today I'm going to be talking, as Dave mentioned, about the application of a new method that we call smooth dynamic warping. And we use this method to increase the accuracy of VPVS ratios that we estimate from time shifts that align events in a PP image with corresponding events in a PS image. So the VPVS ratio is an important attribute for interpreting lithology and fluid properties, and image alignment or image registration is a crucial step in multi-component data analysis. So image registration is complicated by the fact that a PS image is not simply a time-shifted version of a PP image due to differences in noise and reflection waveforms. However, the time shifts are related to the integral of VPVS and thus are often smoothly varying. So therefore, we take advantage of this inherent smoothness and compute time shifts using this new smooth dynamic image warping algorithm. So first, let me show you some results of applying this to some 3D seismic PP and PS images. So here's the PP image that was provided by Geokinetics and Geophysical Pursuit. So this image is showing three different panels that show slices through the 3D image. So the bottom panels are showing inline and crossline slices, and the top panel shows a time slice. And here's the provided PS data. And note that events in these images are approximately visually aligned because I've chosen a timescale for the PS image to make that so. But the PP image is displayed down to about 2 seconds and the PS image down to about 2.8 seconds. And note that the PS image is pretty different than the PP image. It's not simply a time-shifted version of that PP image. And so we use smooth dynamic image warping to compute time shifts. And so the idea here is that for every time in the PP image, there's a corresponding time in the PS image. And the difference between those two times is what we call time shift. And here that's displayed in color. And so we use these time shifts to warp the PS image. So here is the PS image after automatic image registration. And for comparison, the original PP image. So you can see they're both now on the same time scale, and our method has done a pretty good job of aligning a lot of these strong events in the image automatically. So we use these time shifts to warp the PS image to the PP image, but we can also use them to compute VPVS ratios. And throughout this talk, when I'm referring to VPVS ratios, I mean instantaneous or interval VPVS values, not average VPVS values. So now I'll go into a little more detail of these steps. So for PP and PS registration, I'm going to take a single trace extracted from the PP image I showed you previously, and I'll denote that as F, which is a function of PP time. And likewise, I can take a single trace out of the 3D PS image, and I'll call that G, which is a function of PS time. So again, you can see that the time scales here are different, but events in these two traces are approximately visually aligned. So for an event in F at time TPP, we have a corresponding event in G at time TPS. And again, the time shift is the difference between these two times, and that's what we want to compute. And if we know the time shift, then we can say that F is approximately equal to G as a function of PP time plus the time shift U, which varies with PP time. So this time shift will compute with smooth dynamic warping. So as Dave mentioned, smooth dynamic warping is a modification to the dynamic warping algorithm that he talked about last year. And now I'll show you with a synthetic example how exactly we modify this algorithm and how this modification helps to improve the accuracy of our results. So here are alignment errors computed from a synthetic PP trace shown in the bottom panel and a synthetic PS trace, which I'm not shown here. So don't confuse these traces with the ones I showed earlier, extracted from the seismic images. This is now a synthetic example where I know the answer so we can evaluate the accuracy of this method. So for these alignment error plots, the horizontal axis is now pp time and the vertical axis is time shift. And dynamic warping computes a globally optimal solution to a nonlinear least squares problem with many possible local minima. And in this context, the least squares refers to minimizing the sum of alignment errors along some path through this image. So this is really an instructive plot to look at because dynamic warping will compute a path of minimum error that corresponds to the time shifts we'll use to align the PP and the PS trace. It may be difficult for you to, or impossible to see that minimum path right now, and that's partially due to the fact I've added noise to this synthetic to make this a little more interesting. But before we get into that, let me first show you exactly what I mean by alignment errors and how we construct this plot to make this a little more clear. So the bottom trace is still the synthetic PP trace, F, and on top of that I plotted the synthetic PS trace, G. And so to compute alignment errors for a time TPP, we take the squared difference of an amplitude in F at time TPP and amplitudes in G over a range of time shifts. So for example, to compute the alignment error for a time shift of 0, we would do something like this for half a second, for 1 second. And so I'm only showing you 3 time shifts here to illustrate the point, but of course we would do this for all time shifts in between. And so this is how we generate a single vertical line of alignment errors in this image, and we repeat for all PP times to generate this plot. So hopefully that makes this plot a little bit clearer. And now, so I said this was a synthetic example, so I know the answer. So these are the known shifts that I'm displaying with this dashed white curve. And now if I toggle back and forth, maybe you can convince yourself that you see this path of minimum error in the original alignment errors plot. And from this known shift curve, we can compute VPVS ratios, which I'm now showing in the bottom panel with this dashed red curve. So notice that as the slope of the time shifts decrease, so too does the value of the VPVS ratios. And specifically, the relationship between VPVS and time shifts is given by this equation, where VPVS is equal to 1 plus 2 times the derivative of the time shifts u. So this equation implies that time shifts are greater than or equal to 0, otherwise we could compute VPVS values less than 1. So we restrict the time shifts to be monotonically increasing. So again, here are the known shifts and the known VPVS curve that we are hoping to extract from dynamic image warping. So if we use the dynamic warping algorithm that Dave talked about last year, we compute this solid curve, which I'm calling the rough shifts, and from that we compute the VPVS ratios shown in the bottom panel in black, which are wildly oscillating. So to see why this is the case, I'll zoom in on this white box here. So again, the dashed curve is the known shift curve, and the solid curve are the rough shifts. So you can see that the rough shift curve has only 2 different slopes, 0 and 1, and from the equation for VPVS, that explains why we get VPVS ratios of only 1 and 3. And this is due to the fact that we use this computational stencil to accumulate alignment errors. So I'll zoom in even closer so you can see that the stencil only allows 2 possible transitions of 0 and 1. And that's because we're computing time shifts at every time sample. And so this sampling interval I'm going to call h, which in this case is equal to delta t, the time sampling of the data. So the idea with smooth dynamic warping is simple. We'll modify this stencil by increasing h, and now we will accumulate alignment errors by summing along these piecewise linear trajectories. So the minimum and maximum slope in this case is the same as before, 0 and 1, but now we have more finely sampled slopes in between. And using this new stencil, we'll compute time shifts at only coarsely sampled PP times. and we'll interpolate the time shifts in between. So the kinks in this solid curve are the locations where we've actually computed a time shift using this new computational stencil, and the solid curve was obtained from piecewise linear interpolation of those values. So again, just to emphasize that the main idea with the smooth dynamic warping algorithm is that we'll accumulate alignment errors by summing along piecewise linear trajectories at a coarser spacing, and this allows us to more accurately estimate the changes in time shift or the slope of these lines, which in turn allows us to more accurately estimate the VPVS ratios. So the VPVS ratios in the bottom panel in black are still not correct, but it's an improvement over the VPVS ratios we obtained from the rough shifts. So now we can see what happens when we increase this parameter h even more. So here were the rough shifts where h is equal to delta t, now 10 delta t, 25 delta t, 50 delta t, 100, 200, and 400. Now in this last example, we're actually only estimating time shifts at 5 locations and linearly interpolating in between. So here we've gone too far, and we no longer have enough points to accurately reconstruct the known shift curve. But let me go through the sequence one more time and just emphasize the trade-off between accuracy and resolution. So as we decrease our temporal resolution, that is by increasing h, we're able to more accurately resolve changes in time shift and thus more accurately estimate VPVS ratios. So one other point I want to make from this is that, as Dave said, he tried to do this before, as well as a previous CWP student, Luming Liang, who last year talked about automatic registration of PP and PS images and computing VPVS ratios using that method, which I've shown here gives us these rough time shifts. But before he used those shifts for image registration and for computing VPVS ratios, he would smooth the shifts. So if I smooth these shifts, we can see that now we've eliminated the problem where we only had 2 different slopes of 0 and 1, and now by having more slopes, we're doing a better job of estimating VPVS, particularly here after 1.5 seconds. But before that, we're still nowhere close to recovering the correct shifts. So there's no way that we could smooth those rough time shifts in order to get the correct answer in this case. And so the main problem was that the old implementation suggested that we could accurately resolve changes in time shifts at every time sample, which we realized is just incredibly optimistic, especially in this context where PP and PS images have so many differences. So I can show you a quick example of this for the real data that I showed earlier. So here are the VPVS ratios I showed at the beginning of the talk that were obtained from the smooth dynamic image warping shifts. And here are VPVS ratios estimated from rough shifts, rough time shifts that have been smoothed. So you can see similar trends between these two images with high and low VPVS values, but this image shows a lot finer detail, which looks great, but we've shown that this method is far less accurate and that we really don't think we can resolve this fine of resolution from using time shift information alone. So another important thing to consider is the location of these coarse samples. So I'll show you how we do this in 1D. So here is another plot of alignment errors, and now this time this is computed from a PP trace shown in the bottom panel and a PS trace extracted from the seismic images I showed at the beginning of the talk. So using the smooth dynamic warping algorithm, I can compute time shifts shown by this blue curve. So the blue dots represent the coarse, or the location of the coarse samples, and the dashed blue curve represents the time shifts after piecewise linear interpolation. So these blue dots are spaced at a minimum interval h of 160 milliseconds. But note the location of these two of these two blue dots and the corresponding amplitudes in the PP trace below. So an important thing to realize about these alignment errors is that the strong white vertical lines correspond to the high amplitudes in the PP trace, and the strong white diagonal lines correspond to high amplitudes in the PS trace. So we want to use this high amplitude information because these are locations where we have the best chance of resolving changes in time shift. But these two blue dots I've circled are in a location where we have pretty low amplitudes, and there's really nothing in the alignment errors to give us any confidence in these time shift estimates. So in order to take advantage of this high amplitude information, I compute the envelope of the PP trace f, which is given by the square root of f squared plus f hat squared, where f hat is the Hilbert transform of f. And that envelope is displayed in the bottom panel in red. And using this information, I can compute an amplitude-aligned grid that I'll use for smooth dynamic warping, now shown by the yellow curve. So these yellow squares, the location of these yellow squares was chosen to correspond with the highest amplitudes in the envelope of the trace, while also still satisfying some minimum interval parameter. Here in this case, I chose h equals 100 milliseconds. So notice the difference between the time shift curves at these two locations, in particular where we had these poorly placed blue dots from using the regular grid implementation. And it actually turns out that the yellow curve is more accurate in this case. So for 3D, we'd like to do a similar thing so that we can use this for smooth dynamic image warping. So likewise, we could use a regular interval grid that's parameterized by a minimum interval spacing in each dimension. And so these red dots represent the locations of those coarse samples. And using this grid, we can compute these VPVS ratios. But we know from the previous example that we really should be using the maximum amplitude information in our data for smooth dynamic image warping. So that means that we want to select the highest amplitudes that are consistent for all traces in the image, or in other words, we want to select the strongest reflectors in the image. So we can't directly use the method that I just described because reflectors in this image are not horizontal. However, because this image is not structurally complex, we can make reflectors horizontal using image flattening. So here's the PP image after flattening, where all the reflectors in this image are nearly horizontal. And for our purposes, we just try to make the reflectors flat enough for this coarse sampling selection process. It doesn't have to be a perfectly flattened image. So at this point, we can go ahead and compute the envelopes of every trace in the image. And here, red shows us where the strongest reflectors are in the image. And since a constant time represents a single seismic horizon, we can stack all of these envelopes to get a single stacked trace, which is analogous to the problem I described earlier. So now we can select the highest amplitudes in that single trace and extrapolate this to our flattened 3D image. So now we have a reflector-aligned grid in the flattened space shown by these red dots. So all the red dots are horizontal in the flattened space, which is easiest to see in the time slice, but then we can map these coarse sample locations back to the unflattened space, where now these coarse sample locations are no longer horizontal, but follow the dip of these reflectors. And so this allows us to take advantage of the strongest reflectors in the image and use this coarse sampling grid for smooth dynamic image warping. And from this, we obtain the VPVS ratios I've shown you a few times now, which are actually aligned with the reflectors in our image. And so comparing this to the VPVS ratios computed from the regular interval grid, we can see that these VPVS ratios are more consistent laterally. A good example of this is in the bottom right-hand panel, the bottom right panel of this image between 1.7 and 1.8 seconds. you can see a stair-step effect in this low velocity layer where our regular interval grid samples right through that. So this indicates that using this strong or aligning our grid with the reflectors in the image helped us to improve accuracy in this case as well. And so with that, I would like to thank you for your attention, and I'd be happy to take any questions.